If I have seen a little further, it is because I'm standing on the shoulders of giants. Welcome back to the Applied Deep Learning course. Today, we're going to take a look at which shoulders we are standing on and the tools and libraries that we can use to do all the cool things that we've heard in the past few lectures. We're going to talk about deep learning libraries and a lot of practical aspects that are involved in our projects. But before we do that, let me quickly recap from last week's lecture. When is the use of a recurrent neural network suitable? Well, whenever we have sequences and the memory of the sequence can be in both directions is helping us in any way. So if we have a sequence of data where the previous information helps us to understand the current piece of information, it is helpful to have some sort of memory. And recurrent neural networks actually allow us to have something like a memory and therefore are beneficial for these kind of problems. For example, speech recognition is one of these problems, or translating human language. Why are RNNs harder to train than feed-forward networks, even if they have the same depth, the same number of layers? Well, the problem is that with parameter sharing, the input in a simple recurrent neural network just gets fed back into the same layer over and over again. And if you just have a plain recurrent cell, which has one output that is directly fed back into the input, you will have the issue that whatever value you feed in there gets multiplied by the same matrix over and over and over again. So it could happen that your value really kind of shoots out of the window and explodes. So this is kind of challenging here, whereas if you have a feed-forward network, every layer will have a different weight matrix. So, the weight can go up, but in the next layer it might go down again. So you have these different things in a feed-forward network, therefore they're easier to train than a recurrent neural network. LSTMs and gated recurrent units are special types of recurrent neural networks that we took a look at last week. And what they are doing is they're helping us to mitigate this vanishing and exploding gradient. And they're doing it in basically two ways. One way was they're replacing the multiplication, the matrix multiplication with addition. So you have your input signal, you have your matrix, your weight matrix, and you add them instead of multiplying them. And the second thing, what they're doing is that they're introduced gates. And gates are special control mechanisms that control how much information can flow back into your operation here. And the recurrent neural cell here controls these gates. Therefore, it can control how much information it wants to let into the network, how much information it processes inside the cell, and how much information out of the memory that it kind of stores inside, it allows to forget again. So that's how they're helping us to overcome this vanishing and exploding gradients. And last but not least, when do you use connectionist temporal classification? Whenever you have two sequences that are unaligned, that you want to process somehow, where you want to go from one sequence to another. For example, if you have recorded text of me talking and the transcription of text, and whenever you want to train a network to do this transcription, you would use a connectionist temporal classification loss in this case. So it allows us to work with sequences that are unaligned. Okay, now to some new ground that we want to cover this week. First, let's talk about a few machine learning concepts that will affect your practical work quite significantly. And the first thing is called coverage. So coverage means that it is okay to say no, and we all should be aware that sometimes the neural network will be uncertain of the decision. It will not know the answer for sure. And if the system is not confident enough to give a prediction and to state a clear output, it should be allowed to reject giving an answer or saying, okay, please, human, this thing is too hard for me. You have to take over. and delegate the decision to us. And what would be an example how this could actually look like? So when you're producing outputs, for example, for object detection, you could do the following, that the network has a certain confidence for its predictions, and the predictions have a certain threshold. And if the network has confidence below that threshold, it could basically say, no, I'm not predicting an object here. And having this threshold allows the network to do sort of a trade-off, or allows us to do a trade-off where we can say, okay, the network has the chance of not predicting anything. It just has to rate the confidence of these outputs really low, and then we'll cut them off. So the coverage then means it's the number of samples that the network accepted where it predicted something divided by the total number of samples. And ideally, we want this number to be 1. We want all of the samples that are in our data set to actually be predicted and our network accepting them. But sometimes we might have a network that can say, no, I have no idea what's going on. Capacity is probably one of the most important terms when talking about machine learning, and it's because of the following. A central challenge of machine learning is to work well on new, previously unseen data. And how does it do this? Well, we've already talked about this. You have certain assumptions about your data that you're training and working on afterwards, and they have to have the same distribution, and you're trying to learn the distribution from the training set and then apply it to new unseen data. And what in machine learning, what we were talking about, two things. One would be optimization, where we're trying to fit a model as good as possible onto our training set. So we're just trying to minimize the training error. Pure and stupid, just try to get as good as you possibly can on the training set. That would be optimization. But what we want is actually more. We don't want to just have a low training loss. We actually want it to perform well on new unseen data. So what we want in machine learning is to minimize the training error and the generalization error, the test error. The error that we're seeing when we're presenting new unseen data to our network. And a good machine learning algorithm is able to do exactly these two things. 1, make training error small. 2, make the gap between the training error and the test error or generalization error as small as possible. And how can you control this? It's the capacity. This is the central parameter that allows us to determine what capacity our network has, how good it can eventually become and fit our underlying function that we're trying to learn here. So it's the ability to fit a variety of functions. And you can have, as you can see in this example here, you can have underfitting when your model has a too low capacity where it can only predict a line, but our data doesn't reflect. Our data is not coming from a distribution of a single line. So this will be underfitting. We can also have overfitting if we have an arbitrarily complex function that we could potentially fit, then it will perfectly fit this, but will not be likely to correspond to the actual underlying function. So it will overfit on the training set and then perform poorly on the test set. Somewhere in between, there is our appropriate capacity that we're actually striving for and that we would like to have. And how do we know now that we're doing the right thing? Well, we can actually plot our training error and our test error on a graph. And when we take a look at this graph here, we can actually see that the training error goes down over time, but eventually the generalization error goes back up. So that will be the point where we overfit our training data, where we make it work exceptionally well on our training data, but lose the ability to generalize to new unseen data. In practice, for deep learning, what that means is that deep neural networks work best if they have the capacity to easily overfit, but are well regularized. So we're kind of controlling them to not go into that overfitting zone. How do we do this? Well, this will be topic of the rest of this lecture, and there will be a dedicated lecture sometime later on regularization and visualization. The effective capacity that we're actually having in our network can be kind of adjusted by several things. So when we perform regularization, we're reducing the capacity of the model, which can help to optimize it to avoid learning useless functions, and it can ease training and ultimately reduce the generalization error, which is what we want. We want to have a generalization error that is as low as possible. Downside, if we introduce regularization, we are introducing new hyperparameters. And as soon as we introduce new hyperparameters, well, we have to do more work. So the simplest form of regularization would be early stopping. What is early stopping? What we're doing is, while we are training, we're monitoring our performance. And if that performance stagnates and is not getting better anymore over time, I'm going to stop here, because on that set that I'm observing my performance on, called the validation set, we're not seeing any further improvements. And it's a super easy thing to implement. You just have to monitor your performance every epoch or after a certain number of steps. And whenever you haven't seen improvements for, say, 7 epochs, depending on your data size, you just stop and you're done. Another thing when we're talking about the model is, how do we actually increase capacity? So we can increase the capacity, for example, by scaling the model up. We can add more features. We can add more layers, or we could actually increase the input resolution of our data. If we're talking of images, that would be the input resolution, or if we talk about sequences, we could input a longer sequence. So instead of just feeding in 3 words, we could feed in 5 words at the same time to kind of get a bigger window and get more information. And one interesting insight is that the most efficient way of scaling up a model is by doing all of these things at the same time. So their insight was that scaling up the network with depth or resolution does, of course, improve the accuracy because it increases the capacity. The network has the possibility now to fit a more complex function. But that gain that you gain in accuracy and performance diminishes for bigger models. So what you will see in many models that are talking about scaling up or adding more layers is that at the beginning, when you go from 2 layers to 3 layers, it improves the results quite significantly. But if you're having 500 layers and you're going from 500 to 501 layers, the gain that you can still manage with that network is diminishing and going down rapidly. So what they recommend is that you actually have one parameter, and with that parameter, you're scaling up all of these things at the same time. So you're increasing the resolution, you're increasing the width and the depth of your network. And if you're doing this, they say that you're actually getting a kind of the best trade-off between performance and your capacity that you're having in your network. Increasing capacity, adding more layers, yes, but in a clever way. I already used this word before, hyperparameter. Let's talk about this once more to really make sure that you understand what it is. A parameter is a value that we're learning during the training. So a weight in one of our layers is a parameter. A hyperparameter is something that we do not learn, that we actually have to provide, but that controls the algorithmic behavior. And basically, we can either select them manually by just saying, okay, I want to have 3 layers, which if we want to perform such a decision, we need some knowledge and experience. so we can make an educated decision here. Or if we automatically want to determine the best value for this hyperparameter, it becomes computationally expensive. And one really important concept here that I also want to see in your project is that hyperparameters are tuned on a validation set. Now let's talk about the validation set. Typically, when we talk about our entire data set, we've collected, say, 1,000 images that we manually hand annotated for cats and dogs, as usual. And then we say, okay, from these 1,000 images that we've collected, we're taking 800 images, training on them, and 200 images, and testing on them. And if we have no hyperparameters, that would be fine. We can just train on this and test it. The problem is now that we have hyperparameters, they affect our algorithmic behavior and affect the results that we can obtain. So we need to change them. We need to fine-tune this. And the problem is if we only do this on training and test set, we're actually fitting the test set. Do you know what I mean? So the problem would be that I try to train a model with hyperparameters and get whatever results on the test set. But then I'm looking at the test set and I'm changing the parameters to get as low as possible loss on the test set. But we don't want that. We don't want to tune any of our data on the test set. The test set should be something that the network has never seen and that we really separated from our training set to kind of have a meaningful, informed output of how good our how good our network will perform on previously unseen data. And if we do hyperparameter optimization on this training and test set only, we will kind of eliminate this possibility of having a really unbiased decision and unbiased result here from our test set, because we will take a look at the test set and then tune the hyperparameters. So what we can do instead is that we take our training set and we split it again. We split our training set into a set that the network is allowed to see and a set, the so-called validation set, where we're actually tuning the hyperparameters. So we're trying to find good hyperparameters and we're pretending the validation set is our test set. So we're training on the training set and making sure that we're performing as good as possible on the validation set. So we're changing the hyperparameters and doing the same thing again and again. And eventually we will have a good set of hyperparameters. And then, and only then, we're actually evaluating our network on the test set of data that it has really never seen before and that we not have kind of fine-tuned our network to perform well on. The learning rate is probably the most important hyperparameter that you will encounter when you're training your network. And it is the step size that we're moving along in our landscape. And the problem is if it's too large, gradient descent could actually increase rather than decrease the training errors. So the problem is that we take steps that are so large that we're stepping over the valley and onto the next hill. And then, we have to go the other direction again. And this could actually be very problematic in such a way that our network does not learn anything at all. So a learning rate that is too large is a big issue. And if the learning rate is too small, what you probably already assumed was that your training will be very slow. If I want to go downhill and I'm only allowed to take like one tiny step at a time, it will take me a long way to get anywhere. So one thing that you will see is if the training error actually increases, then this happens if the learning rate is at least twice of the optimal learning rate. In other words, if your training error increases instead of decreases, try using half of the learning rate that you've used before. This figure here shows this quite nicely, that your training error, depending on your learning rate, will go down to a certain point and eventually it will explode again. So you won't be able to get a good training error if your learning rate is too high. And that is kind of a sharp cliff. And if you find that point, use half of that learning rate. Selecting hyperparameters is quite challenging and is what makes a good machine learning professional into a really good machine learning professional. If you know how you should tune your hyperparameters. And you sometimes need some experience with how to do this. But first of all, you need to have some knowledge on the effects of these individual hyperparameters. And one would be the number of hidden units. If you have hidden units and you increase that, you increase the effective capacity. If you want to have the ideal capacity, you should find that sweet spot of the learning rate that we've seen before. It shouldn't be too high, it shouldn't be too low, it should be at that optimal value. The convolutional kernel, if you use convolutional neural networks, is also affecting our capacity. And if we have a larger kernel, we increase the capacity. Why? Because the network is able to see more as an input. But it has a caveat, because if you have a bigger input kernel, like a 5x5 or 7x7, you actually hurt performance because it's much more computationally demanding to have these large filters. So what the basic recommendation is that instead of having convolutions with large kernels, is to have multiple layers with smaller kernels. Basically a 3x3 kernel is what is mostly being used for image processing. Implicit zero padding is what we've seen before, that you kind of, if you have an image that you're padding around to make sure that you're always seeing all of the data and not losing some information. So obviously you're increasing capacity when you're doing this. And weight decay is also something interesting. Weight decay is that you're limiting your model parameter values. And basically by introducing weight decay, you are doing the opposite effect. You're reducing the capacity because your output parameters, because the parameters can no longer become very large. And one more hyperparameter that we're talking here is the dropout rate. So that's also one way of regularizing your network, is by using something called dropout, where you randomly deactivate certain neurons. And if you increase the number of neurons that you're disconnecting temporarily, you're also decreasing the capacity. How can you search good hyperparameters? I think I briefly mentioned this already before. So you can either do a grid search. So you have, say, two hyperparameters that you want to tune, and you have a certain range where they can move. You can just kind of form a grid and try one training with each of these values from this grid, or you can do a random search. And the basic insight is, when you are performing random search versus grid searches, that you typically obtain better results with random search, because as you can see here, you might have one parameter that is pretty unimportant and another parameter that is important. And when you do random search, there is a good chance that you will hit that sweet spot for the important parameter. Whereas in the grid search, you're probably wasting a lot of time on unimportant parameters. So in the left figure here, you can see the leftmost column. The important parameter is far away from its ideal value, and we're still trying out unimportant parameters. So I would recommend that if you do a hyperparameter search, that you use a random search mechanism. One way how you can perform hyperparameter optimization is by actually automating this process. And if you think about it, the selection of hyperparameters can be formulated in terms of an optimization problem as well. In that case, the costs that we're optimizing is the validation set error. So we're not optimizing on our training set, but we're actually optimizing the validation set errors. The problem for this is that the gradient, if we formulate it like this, is rarely available. Therefore, we need some alternatives for this. And one big issue that we have with automatic hyperparameter optimization is that it's extremely expensive to run, because you will have to run one complete training per update step. If you think about it, you take one set of hyperparameters, you run complete training, you obtain one piece of information, your validation set error, and then you can run the next thing. So this is an enormously expensive process, even if you're running on a small playground example. However, I recommend you to have a look at it. There are some libraries, and it's subject to ongoing research, how to improve this, how to make this better. So AutoML, AutoKeras, AutoPyTorch are all libraries where you can definitely run some examples and try it out. Just note that it's extremely expensive to perform this automatic hyperparameter optimization. One more term that you should be aware of is the so-called Bayes error. So an ideal model, if you think about it, would be an oracle that simply knows the underlying probability distribution. And whenever you show it something, gives you more or less the correct answer. But even if you have such an oracle that knows the underlying distribution, the problem is that you can still have errors. Why? Because there can be noise in the distribution that, even if you know the true underlying distribution, the sample that you're drawing your examples from can have some noise. And you might actually run into the issue that you have knowledge of the underlying distribution of the variables that you're observing, but the actual output is affected by variables that you cannot observe or that you are not observing. And that can have an influence too. So you will always have a certain error here, and that is called the Bayes error. And one example would be trying to teach a machine to classify whether a cartoon is funny or not. So let's see, is this cartoon funny or not? Well, how would a machine do this? The problem is, sure, it can read the text, it can try to understand what the content is here, but what it cannot do is understand and learn our perception, our background knowledge. And this is something that an algorithm would need to understand whether this cartoon is funny or not, because it's subjective to the viewer and not objective in that image, whether people find this funny or not. So if you want to kind of train a classifier on funny or unfunny cartoons, think about this Bayes error and that you probably will not be able to solve this issue. Some of the practical aspects. When you're designing your machine learning algorithm and your pipeline, I would recommend you to do it in the following way. First, determine your goal. That should be your first priority. You should come up with an error metric and a target value for that error metric. Think about something that makes sense for you and for your problem. For example, if you're doing image classification, well, you would like to have a low F score, or a high F score, or kind of a high accuracy of that classification performance. If you're translating languages, you want to have a low word error rate. Anything that makes sense for your problem, this is the error metric that you will be working on, and you should define which value for this is acceptable. If you're talking about detecting cancer, lung cancer, these target values can be significantly different from kind of classifying cats and dogs. So you should really think about this properly and go into your domain and see what would be acceptable there and what isn't. The second thing, once you know what your problem is, what you want to work on, and what the error metric is, try to establish an end-to-end pipeline as soon as possible. Try to do something where you can quickly take some data, run it through your neural network, train on it, and have something where you can predict something at the end to make sure you can visually verify, or you can verify it all, that you're doing the right thing. Because there are many problems along the way, along building this pipeline, that are not related to your data, but there are some quirks in your code, some bugs. And if you have the full pipeline and ideally some tests for this, you will find these errors quickly before you actually start running large trainings. And you don't want to find a bug in your data loader when you're training on gigabytes of data, but you want to be able to quickly find it as soon as possible, fix it, and only then, when your pipeline runs smoothly, train on the large data set to get the best possible result. Instrument the system to your needs and debug the hell out of it to detect some bottlenecks in performance that could be caused by overfitting. If your model is too powerful here, then what would you do? You would add some regularization. If it's underfitting, you would try to increase the capacity. And of course, there can be defects in the data itself that you're training on, some noise, some incorrectly classified samples, or defects in the software. Your data loader is loading the wrong images. It's loading it from the wrong directory. It's loading always the same image instead of from different directories. So all of these defects, you should be able to spot and debug as soon as possible. And then, once you're sure that your pipeline runs smoothly and you know how you can instrument your thing and debug your pipeline, then I would start to make incremental changes. Gather new data, adjust some hyperparameters, or maybe change your algorithm altogether. If you realize that your network would benefit from an additional input feature, well, go ahead, add that additional input feature into your dataset, and then train again your model. But that is an incremental change where you already will have the complete pipeline. The performance metrics are really important, as I said before, because without a clear goal, well, it's difficult to understand the efforts that you're taking and to understand the effects that any of your changes has on the system. So you should define a goal in terms of a certain error metric or target value that you want ideally to achieve. And in a real-world setting, what error rate is necessary for an application to be safe, cost-effective, and appealing to consumers depends on your domain. So you will have to come up with a meaningful value with your business owner, or just define it for yourself. Because that error metric and target value will guide all of your future decisions. Basically, if you say, I want to achieve 90% accuracy because that's all I need, and you're achieving 94% accuracy, you will stop. And you can start working on something else. You can start making it more efficient. You can make it smaller. But you will stop trying to find a better model. So really make sure that you have a proper metric here. Some considerations for the performance metrics: if one kind of mistake is more severe than a different one, you can actually use that knowledge that you have about the problem in your cost function. So what you can do is, if you have, for example, a network with two heads, one would be the classification of an object detector and one would be the box where it says that the object is. And if we were saying, okay, if the box is a little bit off, it's bad. But if the class that it says what is being depicted in that box is wrong, it's even worse. It's much worse. And we can use that knowledge to use a certain weight and penalize the network harder for making classification errors versus some kind of shift in our boxes. And if you deal with rare events, you can definitely consider using precision and recall. And if you forgot what they are, so the precision is the fraction of detections reported by the model that were correct. So kind of the model says 100 things and 90 of them are correct, then you have 0.9 precision. The recall is the fraction of true events that were detected as opposed to all events that are in there. So if there are 100 objects in your image and the network only reported 90 of them, you have a recall of 0.9. And there is a frequent trade-off here between precision and recall. Think about it. If your network is prone to just blurting out anything that potentially could be in the image, it will have a high recall because it will find all of the 100 objects. But there will be many errors. And on the other edge, on the other end, when you have just the most certain prediction of just the top one object that it sees in the image, you will probably have a really good precision because that object will, with a high chance, be the one object that truly shows there. But all of the other 99 objects in the image, it will not pick up. So the recall will be really low. And what you can do now is you can draw a precision recall curve. You can kind of visualize this and then kind of determine a particular threshold and see where you want to go. And people love to summarize precision and recall into just one output metric. Everyone wants to just have one number, and if that number is good, you're done and you can clap yourself on the shoulder. So what they've come up with is, for example, that you can summarize this as an F-score, which takes precision and recall and summarizes that in a single number, or the sum under the precision recall curve. So when you think about this curve, that as you move towards a higher recall, your precision will drop, and vice versa. And you can actually use this curve and integrate and take the sum underneath this curve, and that should also be as high as possible, because ideally you just have a rectangle where you kind of have no trade-off. You will never have that. Therefore, this sum under the curve is a really good metric here to kind of be meaningful for your metric. One thing that kind of goes into this idea of summing the values under the curve is the average precision if you're using object detection. And it's basically the idea that you're summing the curve under this precision recall thing for each class. Before you start developing your machine learning models, you should actually try to establish a baseline. Maybe depending on the problem that you're looking at, you could try to do something without deep learning in the beginning, run a k-nearest neighbor classifier, do some manual programming and see how fast and how far you can get with that. And depending on the structure of the data, you should start, we have now these three types of layers where we have fully connected layers, where we have fixed size vectors input. So if the data that we're using has a fixed size input, we could start with fully connected layers. If we have grid-like input data, we could use convolutional layers to start with. And if we have some input and output sequences, recurrent neural networks are probably the best starting point to establish a baseline, to kind of get our first draft, our first end-to-end pipeline. And as I said before, the first baseline doesn't have to be any good at all. It just has to run through and output something. You want to have some results at the end of the line. And if that has an accuracy of 20% only, that's fine, but at least you have something that you can improve gradually afterwards. For picking a certain architecture, try to check out different works that are published in the research community on similar problems, and I would recommend to just copy over their architecture or the idea that they're using in their architecture. You can downsize it, often quite significantly, especially for starting. You want to have really small networks to kind of be able to run it on your CPU and debug the data, and then adapt it. And that adapting will be the goal of, if you're bringing your own method, that will be your main focus in your project. I would recommend that you start with vanilla stochastic gradient descent. As we know, it's mini-batch gradient descent, but people often just say stochastic gradient descent with momentum. We also have seen y, and use mild forms of regularization. Even in your first baseline, something like early stopping, you should definitely put into your training loop as soon as possible. One of the things that will help us most along the way is if we can increase the training set size. So one of the problems is that if we have too little data to train on, we would like to kind of understand the underlying distribution, but we can't because we have too little information. So the network will try to fit a curve here, as you can see, but the true underlying distribution is not really what the network will actually learn because it just has too little data to extrapolate onto that underlying distribution. So if we add more data points, we can actually mitigate this issue and improve the quality of our network. And in deep learning, it's one of those things where having more good data that comes from our underlying distribution and is independent is always better. The only downside is that it's not always feasible to add just more data because, for example, when you're working in the medical domain, it can include human suffering, and we definitely don't want more humans to suffer just to get some more data. If you're, for example, looking at illnesses or certain diseases, well, the images of their X-ray scans, you will only get those if the people are sick. So ideally, you would like to find some other ways to improve your network performance than having more people being sick. So a small guideline here for you on trying to answer the question whether you need more data or not. So usually you should start with whatever training set you have and you perform some hyperparameter optimization on your validation set, and you get a certain training error. When your training error is low, well, you go to the next step, to the hyperparameter optimization and testing. Ideally, if you found a good set of hyperparameters. If the test error is low, well, congratulations, you're done. You found a good model that works well on your data. It doesn't necessarily mean that it works well on all of the data, but at least on the data that you have collected and showed to the network. If the training error is high after training, if it can't get to a low training error, well, our network has some issues. It's probably not powerful enough. So the model size, if it's too small, you should increase it, add more layers, make it deeper, or kind of increase the resolution. If it is already large, so if your model is already really powerful and you can still not get to a low training error, maybe take a look at your data, because your data might have an issue now. If your data quality is poor, clean it up. I cannot stress this enough. Having clean and properly annotated data that you're training on is super important. And you should spend some time on assuring the quality of your data is really high. If it's poor, clean it up first and then go back to start and train another round. If the data quality is already good, now it comes kind of to the tricky area. Well, try to gather more data. Maybe you've just not gathered enough data to have a proper learning experience here with your network. And if you can gather more data, do it. If your test error is high, so the training error got down low, but the test error was high, you can try to add regularization or reducing the model size, which would in fact also be one form of regularization, and then again see whether you obtain a low test error now. And if the test error remains high, also try to gather more data. So gathering more data is something that is always beneficial here. And only if you cannot get any more data, well, then you should try to research some better learning algorithms and maybe use a different approach for your problem. Because machine learning and deep learning is not the silver bullet, and there just could be some problems that we cannot solve with this approach that you might be working on right now. When you have your network ready and you run into some issues, you should start debugging and trying to find the reasons why your system is performing poorly. And there could be intrinsic problems with the algorithm itself. For example, that you've just chosen the wrong type of layers for your problem, that you would need some sort of memory, but you're not having that because you're using a convolutional neural network. So there could be some intrinsic problems with the algorithm, or there could be a bug in your implementation. And the second thing is quite likely that you will encounter some of these in your project. So one of the unfortunate things actually with neural networks is that systems are adaptive and they can compensate a lot of human errors. So even if you throw a bunch of garbage in there and kind of play around with non-ideal hyperparameters, you can still get some actually good output results there. So they can compensate for many of the broken parts, for example, dead neurons. So you can have some neurons that are no longer sending any output signals, and still you can perform very well. And the one example that I'll never forget was at one conference, they were showing, that was a really weird paper that they presented, where they were really proud of their network. And what they were doing was that they took an image and they encoded it in such a way that they created so-called superpixels, but it's not what you might think of superpixels, but they created a 3x3 cluster where they kind of had an encoding of the color information of each pixel or of each grid into a certain pixel of that 3x3 grid. And when you ran your image through that, you obtained just seeming like something that looked like noise. And the presenter was really proud of the results, so he got some good results. And then he did a grave mistake. He actually showed us the activations of the first few layers. And guess what? The first few layers of the neural network actually just learned to decode their shitty encoding. So whatever they kind of put in there into these individual pixels, the encoding, the noise and the encoding, the weird thing that didn't make any sense on the input, the network actually was able to compensate for. So really, you shouldn't play around with things if you have no idea what you're doing. And that's why we're here in this course, to kind of get you a better grasp on what you should do. One of the final thoughts on debugging here is that debugging neural networks is inherently difficult because we basically don't know the intended behavior. We can't look into the neural network and say that neuron should have fired. So this is one of the problems with debugging neural networks. One example here that I'd like to bring that was from one of my research papers. So what you can see here is the output of an object detector for music scores. So it's kind of drawing bounding boxes around each notehead, around each line, around each clef at the beginning. And what do you think is the performance that the detector, the output metric that the detector had here? I mean, I'm pretty sure there are some errors in here where maybe some noteheads were missed or some things were not perfectly on spot. So what do you think the network performance is here? I can tell you it's 35% mean average precision, which, if you think about it, 35% for this, like it looks like it got everything right. Maybe it got something twice or it missed some small things, but why is it only having 35% mean average precision here? Well, the reason is that the mean average precision, how it's being computed, might be an unsuitable metric here. It might be difficult to take this as a good statistical value for small objects. Because if you have a small object and it's a little bit off in object detection, you can actually get a low value of the mean average precision without the results being that poor. So you should really think about your metric and if it makes sense on your data. A few more debugging strategies, which I've just shown you. Visualize the model in action. Try to kind of see what the actual output of the model will be and whether it makes sense and how good it actually kind of feels. It's a bit of a gut feeling, but maybe your gut feeling tells you that the metric that you're relying on is inappropriate. What can also be very helpful is if you visualize the worst mistakes that the network makes. So if you have a classifier, please create a directory and give me all the samples that were misclassified. And I have one example where I was training a neural network to do classification on manually annotated data, and it turned out all of the error cases that the network produced were actually human annotator errors. So the machine was saying the right thing because it learned the underlying distribution correctly, but the human annotators made some errors. And of course, there was a mismatch between what the network predicted and what was actually in the image, or what the network predicted and what the annotator said was in the image. Try to reason about your software using this train and test error. You now understand the capacity, you can understand how this behaves, and if you visualize your training and your test error, you can kind of get some insights into how your network is behaving and how it's doing. You should always start with a tiny data set first, just a few samples to kind of make sure everything is running smoothly. And as I just said, monitor your histograms and other important metrics. So let's talk about a few libraries that we can actually use for training our models. I'm pretty sure you've already started using one of them. So let's go through some of them. Large-scale deep learning has a philosophy of connectionism. So one neuron is kind of stupid, but if you have a large population of neurons, they can actually be resemble some sort of intelligence. And nowadays, most libraries exploit the graphical processing unit, your graphics card, to perform operations in parallel because they're specialized for running many parallel computations at the same time. And if you have a matrix multiplication that should be repeated over and over again, graphic cards are excellent at doing exactly that. That's why general purpose graphic processing units are often programmable with CUDA, and deep learning frameworks are heavily making use of this to speed up training of your neural networks. There are many libraries on top of CUDA that kind of have this high-level concept of layers and even more higher concepts of just having a classifier out of the can that you can use, which allows you to do some rapid prototyping and distributed learning, which is a really cool thing when you have a problem that is too large to train on a single machine. You can actually split your problem into multiple parts and train on many machines. And these deep learning frameworks allow you to do this often quite easily. One of the most popular deep learning frameworks is TensorFlow. I think it is the number one in terms of stars and forks on GitHub. So it's being backed up by Google, and they're promoting this quite aggressively. It's primarily developed by the Google Brain team, and it was initially a library for efficient data flow and differential programming, where you were able to kind of compute those linear algebra operations efficiently. And nowadays it has grown into an immensely large ecosystem for machine learning. And you can do many things with TensorFlow. You can efficiently compute all of these mathematical operations that it was initially designed for. And how it does it is by having a computational graph. So you define the operations, and internally it constructs a really efficient graph and then kind of shoots your data through this efficiently compiled graph. It offers many tools for loading and pre-processing data. It has a bunch of high-level functions that you can kind of use on top of these simplistic functions to build, train, and reuse neural models. One of the coolest things is their toolkit for visualizing results, the so-called tensor board, which is used across frameworks. So even if you're using PyTorch, you're frequently using TensorFlow for visualizing the results of your training process. And it offers a wide variety of tools and infrastructure for running training and inference on many different platforms and devices. So you can train a model on several servers and then run it on a small device, on a small smartphone that you have in your pocket. Keras was initially developed as kind of a high-level abstraction of the three most popular deep learning frameworks a few years ago, which were TensorFlow, Theano, and I think CNTK was also back then, the Microsoft toolkit, quite popular, and it kind of had this abstraction layer on top of these. But over time, many of the underlying toolkits died away, and Keras was kind of merged into TensorFlow and is now the high-level way of talking with TensorFlow. So it provides these high-level abstractions, what we've already seen, where you can say conv2d, and then you have your layer that you can actually kind of stack together in a sequential network and use for your operations. The second very popular deep learning framework is PyTorch. It's, again, an open source machine learning framework that is tightly coupled with Python, therefore the name. It originated from Torch, which I think was written where you programmed in Lua. And it's given this kind of tight coupling between Python and PyTorch. It's really developer friendly and easy to debug because you can just set a breakpoint and step into the operations of the framework. It's primarily developed by the Facebook AI research team, and it has two main features. So it's fast and efficient tensor computations that we're doing all of the time. We're using some tensors, some input matrix, and then running it through, computing this, and it can accelerate this with the GPU. And the second thing is that it allows us to train deep neural networks with automatic differentiation. And how it does is it has a tape-based system where it records the operations that it took. So you're running an addition, you're running a multiplication, and it recorded these steps. And when you record and you know that the operation was an addition, you know how to compute the derivative, how to compute the backprop step. So that's what they're doing. So you can kind of replay this to compute the gradient. PyTorch has a rich ecosystem of different tools on top of it. I just want to point out one of them, PyTorch Lighting, which I personally am using, and I enjoy using it quite a bit. It's a framework for writing cleaner PyTorch code, and it allows you to easily run code on different hardware, to switch more easily, because if you're using plain PyTorch, you have to kind of take care of this yourself to move data to the graphics card and back, which is nice in a way that you have to be aware of what's going on, and it makes everything very explicit. But when you're training and doing research, you often don't want to take care of this boilerplate code and just directly want to train your model. So it helps you to kind of focus on that. It helps you on logging, checkpointing, computing some error metrics along the way, and gives you some of the nice tools like early stopping and visualization almost out of the box. You kind of get this really easily by just adding one more line in your code. So it is a really nice framework on top of PyTorch that allows you to focus on designing and doing research with different machine learning models. Fast AI would be a similar project where they also have a high-level library for deep learning that is also built on top of PyTorch. So I would say it's also very useful maybe to even use them in combination. It provides many tools for stuff for operations that are repeatedly written for no reason. So people are writing some data loaders over and over again. So what you can do here is take the data load that they've already written and test it, and that is proven to work efficiently and load your data efficiently, or some data augmentation if you're working with images. They already provide many of these things out of the box that you can use. One more open source framework that was quite prominent is MXNet, which was developed initially by Amazon, then moved over to Apache, and as of 2023 suffered a similar fate as the CNTK framework by Microsoft and is now retired. So I actually recommend that you do not use this framework anymore. Another quite interesting initiative is ONNX, the Open Neural Network Exchange format. It's an open format specification that defines how to represent deep learning models. And the idea is that if you have such an open format, it allows to make deep learning models, trained models, somehow interoperable between many frameworks. And there is a consortium of quite a lot of companies that are supporting this initiative. And the idea is that you can then switch from one framework to another and run your trained model on another kind of execution engine. One thing that I would like to point out here is that Google is quite prominently absent from this list. So Google is a quite strong player here, and as far as I can tell, they've decided to not join this effort. So I guess they rather like you to stay within their ecosystem. And there are quite a few importers, so you can move to TensorFlow, but once you're there, I guess they want you to rather stay in that ecosystem. Maybe in the future this will change. I don't know when you're watching this video. Maybe Google has joined this effort, but as of now, this one is not here. Another quite interesting initiative is Ivy, open source machine learning framework that appeared a few years ago that tries to unify different machine learning frameworks on a maybe a little bit different level, namely on the code level already. So what they're doing is they offer conversions between different frameworks, so between TensorFlow and PyTorch and vice versa. So they take an existing code kind of and transpile it into the different language, so you can use that code in the other language. And if you want, you can even write your code in a framework agnostic Ivy language, sort of, and then decide which backend, for example, PyTorch or JAX or TensorFlow, you want to actually execute that code. And the idea that underlies here is that they adhere to this Python Array API standard that they promote actively, and therefore they're trying to put an umbrella over this. It is quite interesting, this effort, because we have had a similar tool several years ago with Keras, which also exactly tried a similar approach to have a high-level API, a high-level language where you specify it in a kind of framework agnostic format, and then only decide which backend you want to execute your code with. Back then for Keras it was TensorFlow, Theano, and CNTK. Nowadays Keras is fully integrated into TensorFlow, but let's see how Ivy develops in the future. Hugging Face is also a great platform that I highly recommend you to check out. It's actually really a platform. It's an open source community with lots of reference implementations of popular deep learning methods. So you can go check out some existing code there. It offers some Python library for running some pre-trained models. It also features access to a large range of public datasets. And the library that they offered is called Transformers, not to confuse with the architecture of Transformers. But nevertheless, I highly recommend you to also go and check out their resources, even if it's just for learning about existing frameworks and reference implementations. One more quite cool tool that I've found is Ray, which you can use for scaling and hyperparameter optimization. So it's yet another framework that offers you or has the goal that making AI more scalable, and especially making your Python application more easily scale when you do distributed learning. So often you want to run your machine learning training not just on a single computer, but on more resources. And they offer a library that can offer you to take over the heavy lifting of how you distribute this there. They also have what they call Ray Tune, which can be used to simplify hyperparameter optimization. So there you specify your objective, which metric it should optimize, and a search space, as we've seen previously. So you say which values it should search and which kind of search strategy should be applied, for example, a grid search. And then you run this tuner, which runs the full kind of learning loop of your model and then performs hyperparameter optimization here. There are also quite a few libraries for nowadays doing machine learning operations called MLOps, which help you in the long run that if you train your model over and over again to keep track of these experiments, because you have a lot of parameters, you have a lot of hyperparameters, and you play around with your model, you play around with these things, and then you evaluate and get some results. But maybe one training thing was interrupted, another thing, like you had some really good results, but you forgot to write the log somewhere. So the idea here would be that it just allows you to track your experiments, maybe even manage your data sets, do some model versioning to just remain sane when facing the task of training a machine learning model over and over again, to just be able to go back and say, oh yeah, in this with these hyperparameters, I've achieved quite good results. Let's use these hyperparameters or that model that was trained there for my production efforts now. A very popular alternative that you can use for your projects to track your experiments is MLflow. MLflow is an open source platform that allows you to track your experiments similar to weights and biases and visualize the results of your different runs in an interactive user interface. What I personally find really cool about this platform is that it allows you to package your code and ship it in such a way that others can also reproduce your experiments, as part of Docker images, etc. The platform also allows you to store your models and serve your models. Let's sum it up what we've talked about this week. I hope there are some really interesting and helpful hints to you when you're training your neural networks and when you're starting on your second exercise. So let's repeat the coverage. That is the measurement of how often the network rejects to provide an answer. The capacity specifies the capability of our network to kind of learn arbitrary functions. So if the capacity is too low, we would risk underfitting of not being able to learn the underlying function. If it's too high, we risk overfitting to learn kind of too sharp curves of our function and then not being able to generalize well to previously unseen data. And the effective capacity of our neural network is determined by our hyperparameters. And we can kind of tune these hyperparameters, and if the capacity is too high, we can reduce it by adding regularization. The learning rate is the most important hyperparameter, and when you're doing hyperparameter optimization, you're kind of searching for good ones here, perform a random search instead of a grid search, because that's more efficient and you will more likely get a good set of hyperparameters. If you only have time to tune one hyperparameter, go for the learning rate. And gathering more data is almost always beneficial and always a good idea if you're working in an environment where you can gather more data. I know it's not always possible, and it's time expensive sometimes in terms of time and sometimes also of money to gather more data, but there is a high chance that you can improve your performance of your models quite significantly if you gather more data. And finally, there are many libraries that help you to perform these training steps and train efficiently on a graphics card, on a server farm, if you have one of them available, or just on a CPU, and help you to quickly go from an idea to an implementation, maybe in just a bunch of lines of code. And these libraries are what you should use in your project. If you have any questions, feel free to drop me an email. I'll try to get back to you as soon as I can. And I hope that you will have fun with your second exercise and enjoy hacking away your project. See you next week.